Okay, this is Math 1101. It's scheduled to be seen on Election Day. That's Tuesday, November 3rd. Um, Everybody's concerned about the quiz, or actually test, coming up. So the test will be mostly on Chapter 8, which is what today's lecture will be on. We've already started 6.1 on the last uh, video we had, which is available on the cloud. We'll be looking more at attendance on Thursdays, so please be there. Um, Live, not just on the cloud, and we'll try to make that worth your time. The test will cover a little bit of the first chapter, chapter 4, and then I plan to give you the notes for that. Chapter 8, you can have your own notes, but I will not provide those. I will give you a good study guide here right now, however. I think it'll be a good one. And I expect to get a little bit of chapter 6.1 in as well. Something about box plot or 5-number summary, things like that. I have more of an emphasis on multiple choice questions, but there will still be places to show your work. And yes, I will need a PDF from you, hopefully inside of Blackboard, at least by email. Second choice would be email. But if you don't give me anything, then you've got to be prepared to type a lot of stuff in those problems where you have to show your work. A few people did it fine. Many people did not, so I cannot recommend that. I recommend that you send me a PDF of your handwritten work, number your problems. You don't have to do them in order, but you do have to number them. Some people did not do that. You made me guess, and then I don't feel like guessing so much. Okay, let's see why this is zapping out. Okay, so I have to make sure I keep power on here. I lost power just recently. I hope this doesn't happen again. Well, I'm going to go through the chapter quiz, and yes, we did have stuff on the chapter summary at the end of the chapter. I have it on page 593. It's not on the screen right now. But 8.1, as we go through the 4 sections, measures voting power. Does my vote count? Very appropriate. We'll even have a lecture coming up soon on Can We Believe the Polls? That'll be a little bit past the election, but at least we'll have something on that for you. And so we will take a look at 8.1 for a moment here. Voting power is more complicated than may appear at first, and the number of votes required to decide the outcome of an election is the quota, which is typically the majority. For us, I think it's always been the majority. Technically, it could be a plurality. And we have things like the Bajov Power Index and the Shapley-Shubik Power Index. We'll have examples of both of them. And coming up right now, the Shapley-Shubik Index has to do with the power at the swing voter. That'll be problem number 2. And problem number 1 is simply the Bajov Power Index. And so we're going to take a look at an example of that right now. But as you can read, number 1, suppose there are 3 delegates to a small convention. Let me see if I can increase the size here a little bit. Not too much, doesn't want to stick. Okay, so Alfred has 10 votes, Betty has 7 votes, and Gabby has 3 votes. A simple majority wins. Find the quota. The quota is actually the easy part. We have a total of 10 plus 7 plus 3, which is 20 votes. Now, half of that would be 10, but 10 is not a majority. So you add 1, you get 11. That's the majority, and for us, that's the quota. That's what it takes to win. Make a table listing all the coalitions. Those are the groups of people, whether they're simple single people or pairs or even all 3. We're going to ignore the coalitions with 0 votes in them. Technically, that's a coalition too, but we're not going to go there. And so we want 11 votes. We have A for Alfred, B for Betty, G for Gabby. And the first one is for all of the votes. And yeah, of course that's a winning coalition because that's unanimous. But the thing is, the critical voters are the ones you can't live without. And it turns out you can live without B and G. Why? Well, if you take out B, so I'll just put a little line through B, then you still have A plus G, which is 10 plus 3, and that's a majority. And you take out G, put a little note here, G with a slash, and then you have A plus B, that's 10 plus 7, and that's a majority too. However, if you take A out, then you're down to 7 plus 3 is 10 for just B and G together, and A is a critical voter because we have to have A. A is a critical voter. You can't live without A because they've got half the votes. Not a majority, but half. Now, it turns out the next couple of pairs, they're all critical voters because AB by itself is 17. 17 votes. And yeah, that's a winning coalition, and you take either one of them out, and you do not have a majority anymore. So they're both critical voters. That's very typical to have every voter a critical voter in these types of examples. The AG example, 13 total votes. Winning coalition, absolutely, but you can't live without either one of them, either A or G. Take them away, don't have a majority. The last few are not really winning coalitions. They're no's. So the bottom four, A almost got it by itself, 10, not quite. If somebody has a majority by themselves, there's not much to do, by the way, so they don't usually give you problems like that. B plus G adds up to 10, very similar, and we don't have any critical voters because we don't have any winners here. Down here, we've got the losers, so, and B by himself is, or herself, Betty, herself is 7 votes, not enough. G by themselves is 3 votes, not enough. So that's the full bonds-off index, so let me circle that. Then what we do is we look at the total number of critical voters, all 5 of them, and then we look how many times Alfred, Betty, and Gabby showed up. Alfred shows up 3 times out of 5. 1, 2, 3, 4, 5. Count them up. There are 5 of them. So 3/5 is what Alfred has. Much more power than Betty or Gabby. They're not shut out. They each have 1 apiece, as we've already indicated. So basically, you just look at the total and count them up. That's it. Don't overthink it. Just do that. And you've got 3/5, 1/5, and 1/5. Alfred definitely has much more control here. But they don't always line up with the number of votes they have. That's the funny thing about it. Usually it does. Let's go to number 2. I'm a little bit paranoid because the power could go off at any time. I'm not quite sure how this iPad's been going weird on me. Okay, number 2, this is the Shapley-Schubeck index. This is where the swing vote matters, so we get everything in order. And now we have A with 10, B with 8, and C with 3. A little bit different than before. Pretty close, but a little bit different. Simple majority wins. Find the quota, and the quota is exactly the same as before because we have 10 plus 8 plus 3 is 21. You divide by 2, you get 10.5, but of course that becomes an 11. You don't have to add a full number, just get to the next highest whole number, 11, just like before, very close to before. 11 is your quota, and then you put them in all the orders you can think of. I try to do it in alphabetical order as much as you can, such as A, B, C, and then A, C, B, and then go to B, A, C, B, C, A, C, A, B, C, B, A. If you practice this kind of thing, it won't be a problem for you. If you just do it at random and get all 6, fine, but that's could be risky. A lot of people I've found forget about 1 or 2 of them if they don't have a plan. So I would try to go in alphabetical order, librarian style. So now we just see who the swing voters are. Turns out the pattern is apparent. It's always going to be in the second vote. It's just the way this one worked out. And why do I know that? As you go from left to right, you have 10, which is not enough. Then you add 8, the second voter, that's enough. That's 18. All you need to get is 11 for the quota. And so it turns out every time the second voter is the winner, is the one that swings it, so to speak. But you have to look at all the orders. This is not usually practical unless you have a very small system, which happens often enough that this does have some motivation. And then, of course, computers can take over with bigger situations. Well, 10 plus 3, yep, C is the swing voter. 8 plus 10, that gets you over the 11. So in other words, we're looking for it to be greater than or equal to 11. And yeah, once you get to that, it turns out the second vote always does it. 8 plus 3 is exactly 11, barely made it. 3 plus 10, that's 11. 3 plus 8, exactly 11, got it, just barely. So the swing vote is the second vote every time. Here are all the swing votes. And kind of like before with Bonsoff, we just look at the list, see a total of 6. And for example, A has 2 out of 6, which reduces to 1/3. And all of them have 2 out of 6, and they all reduce to 1/3. And there is your answer right there. Now we'll go to the second slide, if I can get there. Okay, it's not letting me do that. Why would that be? Okay, so we just coast on in. Okay, consider the following ranked ballot outcomes. As we go into 8.2, a few words out of the summary. And these summaries are excellent summaries, by the way. If you want to get a way of studying for it, besides the problems I'm writing out, look at the chapter summary. They're extraordinarily good. Voting systems, how do we choose a winner? They have several types of systems. We're just going to focus on a couple of them here. And we're going to try the elimination runoff system, and we're going to try the Condorcet winner. And those will be the 2 that we look at. So problem number 3 from 8.2, there's 2 apiece. So we had 8.1, now it's 8.2. Let me grab a pen that works. And 8.2 is the section we have. And it turns out we're going to have the ranked ballot outcome. And the way they always do it is the last choice gets 0 points. And then the next person gets 1, or the next choice gets 1, and the next choice gets 1 more. And you could go up to 3 or 4 at the top, but we only have 3 choices. It's a 2-1-0 type of a system. The last one always gets 0. I might have done it differently, but they didn't ask me. So we want to find out the winner under the elimination runoff system. Looks like I'm doing the Borda count first. So yeah, I jumped the gun. I'm doing the Borda count first. So let's look at Borda first. And so Alfred, I'll just use A for Alfred, has 7 votes. Notice this is the rank, the number of votes in each of these sort of the coalitions or groups. And A gets 7 times 2 for the first group, and then Alfred gets 0 times 4 for the second group, so plus 0 times 4. It doesn't count for much of anything. And then in the last group, we have Alfred getting 1 point for 3 votes, so plus 1 times 3. So 1 point for being in second place and spread out only over 3 votes. So it's going to be 14 plus 0 plus 3 is 17. So Alfred has 17 votes in problem number 3. Let's look at the next one, B for Betty. And Betty would have, in the first group of 7, she gets 1 point each for the 7s. So 7 voters times 1 for being in second place. It's supposed to be a 1, sorry. And then Betty gets first place, but only 4 votes there. So she'll get her 2 votes for first place times the 4 votes in the second group right there. Now Betty unfortunately comes in last for the 3 votes, so you could say plus 0 times 3. It certainly is a good idea to do that. But 7 times 1, if I can write a 1 there, is 7, and then plus 8. 7 plus 8 plus 0 is 15. So Betty has 15 votes on the Borda count. And finally, Gabby, which is a G, she gets 0 for the first group. 0 times 7. And then she gets 1 point for the 4 group. So 1 times 4. And then for the last group, she wins, but she only wins 3 voters. So 2 points times 3. And so we've got 0 plus 4 plus 6. That's 10. So according to this, Alfred is the Borda count winner by kind of a ranked voting system. That's sort of the one I like the most. And the elimination one's a little bit easier because basically you just look and see who came in last. And Gabby came in last. She only got 10, so basically she's crossed off the list. And elimination says that Gabby is done. And so, that means that we have Alfred versus Betty. Alfred wins the 7 votes there. And then we have Betty versus Alfred. Betty actually won that one. But then Alfred wins again. So 7 voters take Alfred, and 3 voters take Alfred at the end. So that'd be A under the elimination runoff system, which I'm doing last. And then Betty, Gabby's out of the picture, she gets only a win on the 4. So 10 beats 4. So Alfred's the winner on both counts, which is very typically the case in these types of things. Now we have a Condorcet winner in problem number 4. Now that means that as you look at each of the pairs, you have a clear victor along those lines. So let's take a look at how that could go. I'm going to do the A-B first. So you have to have a plan, A-B, B-C, or I'm going to do it in alphabetical order, A-B, followed by A-C, followed by B-C. Okay, very good. This angle on the iPad is a little bit harder to write on. I apologize for that. I wish I could adjust it. It really isn't adjustable. Okay, so then we have the fact that we need to find out how the Condorcet winner would go. As we look at just A versus B, well, A would win. A would get, Abe over Ben would be, as I write this out, AB. Well, A gets how many votes? We got 7 votes here over Ben, and then Abe versus B gets 3 votes, as it's just a one-on-one versus Ben. So you get Abe gets 7. Let me cross this out. 7 plus 3 is 10. Now that's for A. That's for A. Now B only won 1 of them. They won 5. So it looks like A is the Condorcet winner as far as the first pair is concerned. So A wins there. Now, if you win both your battles, then you're the Condorcet winner. So let's look at A again, alphabetical order. I'll do AC. So Ben doesn't count. It's just Abe versus Condi. So as I look at A first, especially, see if you get A to win twice in a row, you're done. And that could make things a little faster, especially on a test. So I'm going to do that part first, just go for one that looks likely to win. So A gets versus Condi, got 7 votes. On the second one with 5, Condi beat Abe. Oops, so Abe loses there, so you could say it's C gets a 5 on that one. But then over at the end, Condi beat Abe again, so she got 5 plus 3, and that's 8. So this time Condi is the winner. Oh boy, so that's A is out. Let's look at B versus C, and maybe we can get C to win twice in a row. Just take a look. So here is Ben versus Condi. Abe does not count. So in the first group for B, B gets 7 votes, beating Condi. And then B wins again. So it looks like that's a winner there. And then we look at the end, it's kind of a revolving, a round robin type of a thing. Now Condi beats Ben on the 3-vote system, and so Condi gets 3. But Ben had 12, so Ben's the winner there. So each of them take turns in winning. A beats B, it's rock, paper, scissors. But C beats A, and then B beats C. So it's like rock, paper, scissors in a way. So that's a little bit frustrating, perhaps. Let me see if I can slide this picture up a little bit. Okay, so that was 8.2. Now we're going to go into 8.3, see how that turns out. Get a working pen. So 8.3. The title of this one, as you can see in your own chapter review, is Fair Division, What is a Fair Share? I do not plan to get into highly involved problems involving a farmhouse and wheat fields and stuff like that. However, you should be able to get basic ones. So the ones that you see on the chapter quiz are definitely fair game. So that's why you should study this on your own and work out other homework problems, especially odd numbers that have answers in the back. I strongly recommend that. I just haven't taken the time to assign them. I'm not sure if the WebAssign has enough problems for you. I mean, they're good problems. Instead of like Chapter 4, they weren't very good, but in Chapter 8, they've been very good. They just don't have enough of them. So I highly recommend if you're after the A here, you should really try to work some of the homework problems, especially those with answers that you can quickly double check. But looking at number 5, the fair division here, we have a simplest kind of fair division scheme is a divide and choose procedure for 2 people. But it doesn't mean equal division. If it just so happens they both put the same number of points and everything, you're done. But that's not likely to happen. So we assume that it is not going to happen that way. So we put down points. And as you see in number 5, Michael put down 40 points for the cottage, and in the beginning won it, and Juanito only put down 30. Michael put down 30 for the penthouse apartment. Juanito only put down 45. But then Juanita put down more of her 100 points. Total is 100 points, by the way. And so she won the Ferrari. So right now we have the Lakeside Cottage going to, let me turn this on, Michael, beating 40 to 30. Penthouse apartment, 30 to 25, gets that. But Juanita gets the Ferrari. They have to put out 100 points, divided up in any way they want. Let's not go into fractions and decimals, please. Let's just go into, the whole numbers. 40, 30, 30 is pretty good. 30, 25, and 45. So the idea is to split them up. And Michael right now has 70 points. So I'll put down M has 70. Picking up the wrong one. And Juanita only has 45. So J has 45. So that's not a fair split. We want to get it closer to 50-50. Now, it doesn't mean 50 points each. It probably means we're like 60 points each. But that part depends on the scenario. So now we look at Mike's ratios. Michael to Juanita ratio is what we're going to do. So I'll call that M over J. Michael has to give up something. Which one is it? So we look at the Lakeside Cottage, and that ratio is 40 to 30. So I'll put down LC, and 40 to 30 is a 1.3. The idea is to pick the smallest one. The smallest one that he owns is the penthouse apartment. So this is a ratio, make that clear, just like we did in the book and we did on the lectures. So the penthouse apartment, I'll call it PA. Okay, it's turning off again. PA has a 30 to 25 ratio. Wow. The battery must be almost dead. 30 over 25 ratio, that's 6 to 5, or a 1.2 ratio. You pick the smallest one. That's the one that we go for first. We have to divide up the penthouse apartment. So we set up the following equation. Well, Michael has 70 points. As you see, 40 plus 30 is 70 points. And he's going to give up part of the penthouse apartment. And that happens to be P for points, but also for penthouse, I guess. And he put down 30 points for the penthouse apartment. So in terms of a decimal, it's 30%. 0.3 would do. They've been putting 0.30. That really does not matter. So that's the part of his equation we start with. And we set that equal to Juanita and her 45 points. 45, and we'll add in the points she assigned to the penthouse apartment. That's only, ironically, 0.25. So I'll put down plus 0.25p. I wish I could write a little bit more clearly for you. I apologize for that. Okay, and every time I touch the screen, something else happens. So we'd use a little bit of algebra. I would subtract 45 from each side. I wish I could show you more. You get minus 0.30p equals 22, or I'm sorry, 25, as we subtract 70 from each side. That's what I'm doing, and then we still have our p's to deal with. And then I guess I would go ahead and add 0.30 to each side, and actually have this backwards here, 70 minus 0.30, and then that's 45 plus 0.25p. And then we have, let's see, I've made a mistake here. Let me cross this out. So we have all of that. So anyway, what it boils down to is that you have 0.55, it's taking too long, 0.55p equaling 25. Do it yourself, basic algebra and work. So p would equal 25 divided by 0.55. Use your calculator and round to the nearest percentage. It's about 45%. Turns out this is a splittable object, and so Michael will get the lakeside cottage. That one had a higher ratio. We're not going to split that up. Juanita won the Ferrari outright. So those two are not being contested. It's the penthouse apartment that we get to split up. And fortunately, that one is actually splittable. There's some that really aren't. How would you share a car, for example? You have it in the winter months, person has it in the summer months. I guess you could do that. But an apartment would be a little bit easier to do. So she's going to get to keep 45% of the apartment. And of course, that means by subtracting from 100, Michael gets 55%. It's hard for me to squeeze that in. So that would be for Juanita. I'll put a little J here. And then, of course, 55% for Michael. I'm not going to write that down, but that's just the leftover amount. Looking at number 6, I didn't mean to fill up all the room here. I mean, I have my room to write here. Ann, Beth, Kate, and Dan wish to divide a computer. And I guess they're going to be sharing it. Use the Naster procedure, different procedure, to fairly divide the computer with the following bits. This is the one that has a kitty in it. And we're only going to do one level of it, not 3, as one of the examples did. So what we have to do, and they've only given you the answers, we have to look at who won the bid. Beth won the bid. It's kind of easy. You see the $2,000 right there. So she gets to keep it, but she has to pay some cash in order to do that. But it isn't as easy as you might think, especially if you hadn't had this class before. What we have to do is to take that $2,000 and carve it up. So the people are going to get a third of their bid, or a fourth of their bid. So we take 1/4 of the bid as we look at number 6. So I'll put my little notes here. 1/4 of the bid. So now I'll put down the people's names: A, B, C, and D. What a surprise! And so A will get a fourth of their bid. 1/4 of 1,200. 12 over 4 is 300. So she gets 300 cash right off the top. You can put a plus sign there if you want to. Beth actually owns 500 of this outright. So technically she kind of pays herself $500, which is silly. C is the same as A, so that makes it a duplicate of A. 1,200 divided by 4, 300. Dan, 1,600. Divide it by 4, 4 people after all. He's going to get $400 outright. So we add all that stuff up and find that's $1,500, which means the kitty, I'll put down K for kitty, originally is paid $2,000. Because first of all, Beth pays the $2,000 cash to get the car. But then the $1,500 comes out of the kitty. There's $500 left. And that gets to be redivided. So this never goes to 0 unless they had a 4-way tie, and that'd be a completely different problem. But because there are not ties here, we're going to have to redivide the $500. So it would be plus 1/4 of the kitty, which is going to be a non-zero number. Sometimes it's a lot, sometimes it's not. I'm trying to write the word kitty here. Put a little meow there. I'll put a little smiley face with like that. And, anyway, so divide this by 4, and everybody gets 125 to finish it off. So 125, 125, 125, 125. That zeroes out the kitty, by the way. So then it's zeroed out. Kitty has to be 0 at the end because kitty isn't really real. Sad to say. I've got a cat right over there, by the way. We do have the totals now, and Ann will get paid $425. Okay, maybe that's not great, but she didn't bid very much either. Let's go over to Kate, same as Ann, gets paid $425. Dan bid more, so he gets more. So the idea is to bid, if you don't really want the car, you bid high, and then you want to be in second place, so you get more cash that way. Of course, you want the car. You bid too much, you win the car, and if that's what you want, great. We're assuming they all want it, and I meant to say computer, not car. So that's the money they get paid. Well, turns out that Beth gets to keep $625, so really she has to pay out because we have a minus $2,000 over here. She's the one that pays. She has to foot the bills here, which is a minus $1,375. But she got the computer. So that's the price she paid for keeping the computer. And that's how the NASTR procedure works. Now we'll go to 8.4. And this one is tough to read, but it'll take up a little bit more room. The city has 4 districts, northeast, west, and south. They're required to be 15 city councilors, like little, managers or whatever you want to call them, allocated according to population with at least one from each district, which is never a problem. Given the following populations, calculate the quota for each district. So let's slide over here and see what we're after. And let's go back down the page and go to number 7. Can't go too fast. So looking at 7, which we're right up here, so let me put a little 7 here to remind you what we're working on. Okay, so what we have to do first, before we talk about Hamilton's, we have to figure out what the ideal district would be. So the ideal district size is pretty easy. It's just a matter of taking the 34,500 people and dividing by 15. That happens to be 2,300 per district, 2,300. So then, to get to Hamilton's method, we have to figure out what the quota would be. What would the numbers be? And that's shown on the next stage here. We got the total. We divided by 15 to get to 2,300 per. And so how they got this number, the 1.8, is as follows. Take your 4,200 in the lowly populated north, divide by the quota size, and that becomes almost a 2, but not quite. It's actually 1.8. We divide everything by 2,300 here. East is quite frustrated because they got 5.9. So 13,500 divided by 2,300 is 5.9. And the West, well, you get the pattern here. 7,600 divided by 2,300. This is exact numbers, which is nice. That's 3.3. And finally, the South, you got 9,200 divided by 2,300. That's exactly 4.0. Okay, so we always round down using the Hamilton method. This is the only one that doesn't adjust the divisor and redivide. But you round down, you just kind of see where the decimal parts go. And as you round down, of course, you're not going to usually wind up where you want to be. It could happen, but it hardly ever does, it seems. So you get a 1, a 5, a 3, and a 4. Only 13. We're missing a couple because we need a total of 15. Then you look at the decimal part. They call it fractional part. That's more traditional Constitution language. And the highest one is a 0.9. The next highest is a 0.8. We were looking for 2. We stopped there. No matter whether it's a 0.5 or a 0.4, it has little to do with it. And the high numbers are going to get an extra seat. Just like rounding up, but not always. We've seen a few cases where it didn't happen. The 0.3 and the 0.0 are not going to be rounded up. They're just ignored. In fact, this is just like Webster's method, my favorite method, where you just simply round it. And that usually works out. Too simple. Anyway, you add them up, and you got the 1 for the north and an extra 1 for a total of 2. You had 5 for the east, and rounded up to 6. It was almost a 6 already. And this goes in kind of a natural way. Nobody's getting really hurt by this one. But you do get a total of 15, and that's the districts that are going to be allocated. The north would get 2, the east should get 6, the west should get 3, and the south should get 4, which is about as appropriate as we can get to the ideal district size. This was actually a pretty good fit here. Nobody's really getting hurt. The west might have gotten hurt the most. It was off by 0.3. and it got actually lost its 3/10 of the quota. So anyway, if there was some loser here, it'd be the West, and if there's a winner, it'd be the North, because they were 2/10 shy, and yet they got rounded up. So anyway, no big deal. Now we have a very similar situation in number 8. And we start off just exactly the same way. It's got the same exact deal, except we want to get Jefferson's method involved. This is where we adjust the divisor. And the beginning part is exactly the same. I wish I could keep the screen on the entire same page. And we get the same numbers, 1.8 all the way down to 4.0. And yeah, to the nearest tenth, it actually rounds to 15, and that works out great. And then we go through the quota rounded down, just like before, and this is all exactly the same as before. That's where it stops. That's where Jefferson and Hamilton part ways. And Hamilton was in a duel with Aaron Burr, but that's another story. I guess we don't go into that right now. So we have to decrease the divisor. This number is too low. 13 is less than 15, which when you're rounding down, yeah, that's going to happen. Hard to imagine rounding up. I suppose it could happen, but not very often. So rounding down, and that means you decrease the divisor. And it turns out as you divide by a smaller number, all the numbers get bigger. Inverse relationship. Dividing by 2 is a lot different than dividing by 10. You divide by 10, you're not getting so much. Divide by 2, well, you're getting quite a lot. So anyway, let's take a look at what happens when they pick these numbers arbitrarily. There are formulas for these, but typically you just pick a nice round number nearby and just see if you can get that 15. And if you do, you're done. If you don't, you just keep trying. And if you go too high, then you will increase the divisor to compensate for being a little too high. So we don't need to break out those formulas. We just divide by 2,000. And so now 4,200 divided by 2,000 is actually pretty easy. Just divide by 2 and move the decimals around. There's your 2.1. So let me put that down. So I'll put it right nearby. They forgot to give us that extra work. And then 13,500 also divided by 2,000. That works out to be, in a rounded way, 6.8. So I'll put that down here too. And then 7,600 divided by 2,000. That works out to be 3.8. I'll put that down here as well. Hard to read my thick pen here. 9,200 divided by 2,000. That works out to be 4.6. So I'll put down 4.6. And now we have to round down, because these numbers, when you add them up, will definitely be more than 15. Do I have that number handy? Let's just find out, for curiosity's sake, what that number would be. 2.1 plus 6.8 plus 3.8. You do not have to do this. I'm just curious. And then 4.6. That adds up to 17.3. They don't bother to go this deep because clearly it needs to be rounded down. And when you do, you just truncate all the decimals. 2.1 hardly moves at all. It's right where it's supposed to be, at a 2. 6.8, they lost out. They're down to 6. 3.8, they lost out too. That's down to a 3. The 4.6, they all kind of suffered. You might think they'd round up. Of course, we did arbitrarily change the divisor too. So this all kind of balances out in a different kind of way. We got our 15. And oh, by the way, the 2, 6, 3, 4 grouping happens to be the same, as 2, 6, 3, 4 up here. So it turns out Jefferson and Hamilton, even though they have different methods, they wound up with the same exact numbers. That's kind of amazing. Have a little time here, and it's possible I could go for simpler problems. Yeah, certainly could do that to round things out. And I thought I'd look at a few of the problems, as I suggest you do, at 8.4. And I'm going to look at just district sizes. This is just simple division most of the way. And 8.4, number 9, this is the homework. I find it on page 591. It's at the end of the reading for 8.4. So still section 8.4 on apportionment. And all that. Am I represented? I hope everybody is. You better be. Of course, if you're a citizen, especially 18 or over. Okay, number 9, if you can read that. It does say district size in 1790. I think we may have looked at this before. We had about 3.6 million people. And I'll just put down mil. And we only had 105 in the House at that point. That's what Congress gets to set. And that's up to them to decide that. And so we had an ideal district size of the following. So we need to find the ideal district size. We did this already a little bit. You divide that out, you get 34,437. That's not very many. In fact, even in the Constitution, they said you've got to be over 30,000, as if that would ever be an issue. I guess they just couldn't foresee the exponential growth that most of the world has gone through. We're certainly not alone in having a much greater population than back a long time ago. So let's just compare that to the latest one available, number 10. Okay, well, we had 309 million back then, and more now. I'll just round this, and yes, you can find the exact digits in the book. And we currently have 435 members. So it's interesting that they've only moved the needle up 4 times. But then you look at, and we've already talked about this in the lectures, we're looking at over 710,767. And I'm dropping the decimals. I know the book likes to keep them. Look at the difference. Now every representative covers over 700,000 people on average. And before it was only 34,000. Quite a bit of a difference there. We mentioned that Montana was getting kind of screwed that way because they had over 1 million in their district, just the way the rounding went. They couldn't quite get to 2 or get probably down to 500,000 or 550,000, but they're right at the border and they just couldn't quite move it over. With this census, it'd be interesting to see if Montana actually does get their second representative that they used to have. It's interesting to see how population changes. It's almost a competing situation. California is likely to lose a representative as well. So out comes the gerrymandering. Both the parties love to gerrymander. I wish they would get rid of that, just have rectangles only, but that's just my opinion. But anyway, let's move back to the problems. No more politics. Number 11. Let's take a look at a few of these. We got New York's quota, and you could take a look at that one. New York only had 332,000 back then, and the district size was that. And they go through and find that kind of stuff. I'll let you do number 11. I've got an answer on that one. Instead, I think I'd be more interested in number 13. Let's just go to number 13. This one's about California. And in 2010, the U.S. population was 309 million. There are 435 members. We have our quota already. That's what we're going to use for the ideal district size. And we look at California's population. I'll say California, and they had 37,334,989 or whatever. So 37 mil, I'll just say 37 mil, and we'll divide by that 710,000. And that's going to get you the number of representatives that California should be getting. And it became 52.54. And I believe they did round up. I don't see the details here, but it looks like we rounded up to 53. So I believe, I'm pretty sure, I'm not 100% sure, I believe we have 53 representatives. And biggest state, and yeah, to hit pretty close to the ideal size. Now, of course, the Electoral College will get 2 more, but the 2 doesn't make much difference on the 53 as compared to a state, I hate to pick on Wyoming, with only 1, or even Montana with only 1. And they suddenly get triple what they would have gotten with 1 plus 2 equaling 3 on the Electoral College. So Electoral College, which is a little different than the House of Representatives. They're similar but different. You just simply add 2. Add 2 to every single state. And D.C. is done separately. They just put 3 in there because 3 is the minimum. So, yeah, California gets 55, but Wyoming will get 3. So, anyway, that throws it a little bit out of whack Electoral College-wise. But anyway, let's look at a couple more here. An interesting house size. U.S. Constitution says that we have to have at least 30,000 in every district. Now, we have, as I look at problem number 15, what would happen if we just kept it at 30,000, just kept on increasing the House of Representatives? It could happen. If you take your 309 million and divide by 30,000 mil, divided by, 34,000, just 30,000. 30,000. And you divide that out and put a few more digits in from the homework, and you get 10,800 representatives in the House of Representatives. And you compare that, if I can spell out that word, it's a little bit bigger than 435, just a little bit. Can you imagine 10,000 representatives, House of Representatives people being in the House of Representatives? There wouldn't be enough room for them. They'd have to have a football field for them to vote. Yeah, that would not be practical. So 30,000, yeah, that's an antiquated number, but it's very, very unlikely we'll ever dip below those numbers. Uh, and then this leads us over towards Washington's veto. We hinted at this. Number 16, this is the very first presidential veto there ever was. And George Washington did it. He vetoed Hamilton's apportionment bill. It did come back 50, 60 years later. So Hamilton did get his due diligence, but it was after he passed away. But Washington didn't like it. And just to boil it down, without all the details, they focused on Delaware. Hamilton's method gave Delaware 2 House seats. Delaware had 55,000 people. So I'll just spell out Delaware. This is back in 1790. They had, we're not going to go through the details of Hamilton's. This is a short one. 55,540. And they got 2 House seats. So they got to represent only 27,770, but that's less than 30,000. This falls below the minimum. And Washington said, hey, there's something wrong with this. You're supposed to have at least 30,000. So he said, okay, Delaware gets 1. And Hamilton, sorry, we're not going to use your method. So they probably went to another method, maybe Jefferson's method. All these people, Adams, Webster, all these people were around, founding fathers and all. So they picked another method. We don't have that right here in the book. But yeah, it didn't work out for Washington. So he said, nope. They did bring it back. So Hamilton was in effect for a few decades there. And now they've got the Huntington Hill method. We're not going to say too much about that. That's just how do you round. It just use that particular mean. I don't think I wouldn't be able to do that without providing a table. So that doesn't look likely that I'd do Huntington Hill here. They do show the graph there on the last page of the reading about how bias towards small states or large states has gone through the decades. And for me, Webster's the best. It straddles the line between being as close to unbiased as possible and just natural rounding. Amazingly, how that does that. It doesn't bias anything. Not really. You'd have to really take it out to several decimals to see any bias, and pretty much right on the line between small and large states. So Webster's my favorite. But anyway, we have all these methods. I wish we could have said more about the Electoral College. In the last 115 class, we had a lot more material on that. But I encourage you to check out the map of 2016, and it will be interesting to see how the map of 2020 shakes out, whether it's real soon or several weeks from now, we don't know. But anyway, we will have a live class on Thursday. Yes, for some of you, I'll be taking attendance. That's going to be the plan. One section, yes, and I'll be kind of alternating around. I'm not picking on anyone. I just want to make sure that we're getting a representative. They encourage us to do all live classes. So that's kind of how that goes. Anyway, that's going to be all I have. Maybe my power's ready to die. So I'm going to go ahead and say goodbye and contact me on the office hours, and we'll talk to you soon. Bye-bye.